Hello, everybody, and thanks for listening to this presentation, which is about robust and risk-aware motion planning in the presence of state estimation uncertainty. I'm Lars Lindemann, and I'm currently a postdoc at the University of Pennsylvania, and this presentation is based on joint work together with Matthew Cleveland, Yanis Kantaros, and Professor George Papas, who are also there. The figures on this slide show examples of autonomous systems that operate in uncertain environments, such as automated warehouses, autonomous mapping and autonomous exploration, or service robots. As these systems are employed in uncertain environments, they rely on sensor information to localize themselves in order to achieve their objectives. While these systems are all different in terms of dynamics and system objectives, they have in common that they are subject to state estimation uncertainty due to noisy sensing of the environment and imperfect perception. Furthermore, these systems are safety critical. In other words, a failure of this system may be costly and in some cases even harm humans that may be present in the proximity of the robots. Therefore, safety really depends on robustness and risk awareness. Towards a risk-aware autonomy, this paper presents a robust and risk-aware motion planning technique under state estimation uncertainty. Over the past years, there has been great interest in motion planning. Motion planning for deterministic systems and environments has been well studied and had great success. And this was especially after the introduction of the efficient and asymptotically optimal sampling-based RRT star algorithm. More recently, interest in motion planning for unknown systems in unknown environments has increasingly gained attention for all the reasons presented in the previous slide. POM-MDPs are general models that describe such stochastic systems. However, in general, motion planning under POM-MDPs is intractable and computationally expensive. Efficient sampling-based methods have been proposed to deal with such stochastic motion planning problems by the introductions of the chance-constrained RRT. More geared towards the theme of this paper, RRT incorporating sensor information such as LiDAR and state estimators such as the well-known Kalman filter have also been studied more recently. A very recent trend is to also consider risk constraints in such RRT frameworks that lets us reason about the risk of violating a safety specification. We continue in this paper along the lines of the previous research, and our contributions are the following. First, we formulate a risk-aware motion planning problem under a Kalman filter. Second, we define a tractable approximation of this problem by a robust reformulation of the original problem, and in particular by robustly reformulating the risk constraints. Third, we propose a robust RRT to solve the approximate problem and discuss the approximation gap between the original and the approximate problem. Fourth, we show how robust RRT is integrated into online planning and control and how more robustness results in less replanning, however, at the cost of more conservatism. Let me briefly introduce risk measures that allow for an axiomatic risk assessment in terms of a cost random variable. Particularly, we're interested in tail risk measures. In the right figure here, we can see a cost random variable where the distribution of the cost is plotted on the y-axis. Shown are several risk measures, such as the expected value, which is a neutral risk measure. Also shown are the value at risk and the conditional value at risk, which are tail risk measures. I am here omitting their mathematical definitions, but the value at risk at level beta indicates that the probability of having a cost higher than the value at risk is less than 1 minus beta. As closed form expressions are mostly hard to obtain for general cost distributions, the risk associated with a cost function is mostly in the literature estimated from data, and I've given some references over here. In this work, we are particularly interested to consider the risk of violating safety specifications, and we consider safety specifications formulated by or denoted by a function d, and the function d acts on the estimated system state and the environment. So what we do then is we take a risk measure and we wrap it around this safety constraint, and then we want that this risk is upper bounded by a threshold gamma. To keep the problem in this paper tractable, we focus on linear systems, such as, for instance, obtained when locally linearizing a nonlinear plant or a nonlinear sensor model. We now can define our risk-aware motion planning problem with the goal to find a sequence of control inputs for this plan that minimizes a cost function and subject to the Kalman filter equations and subject to risk constraints. So let me walk you through this briefly. These equations over here, the mu and the sigma, are the equations, the Kalman filter equations that can be described by a map Fu and F sigma that are omitted here. And these describe the Kalman filter estimate X that is Gaussian distributed with exactly this mean and the covariance, okay? Additionally, we have the risk constraints, and the risk constraints here act on the function d that I mentioned before. It can be a safety constraint, and then on this Kalman filter estimate X over here. We have another constraint, which is a goal constraint, so for reaching a goal, basically. Particularly, I want to highlight here that the Kalman filter equations depend on future state measurements that are not known a priori. And by a priori, I mean that at time 0, when we want to plan a risk-aware path, that no future measurements are available. This makes the Kalman estimate X unknown, such that the risk constraints over here cannot be evaluated at time 0. For these reasons, we cannot solve this problem at time 0 due to missing measurements. We therefore propose a tractable approximation of this problem by proposing a robust reformulation. First, I repeat here the Kalman filter estimate in blue and show a potential sequence of Kalman estimates that may be obtained after observing measurements. Instead of the Kalman filter estimate, again, that is unknown a priori, we use the Kalman filter at time 0 for multi-step ahead prediction, which I refer to as the Kalman filter prediction that can be written like this. These can, for instance, correspond to the black dots that are shown over here and that are close to the Kalman filter estimate, but may not be exactly the same. Now, instead of the risk constraints from the previous slide in the original problem that I also repeat over here, we instead use the Kalman filter prediction and additionally robustify the constraints. In particular, we see in the right the Kalman prediction over here and the operation B epsilon around it. This operation indicates the set of all distributions that are epsilon close to the Kalman filter prediction. So we put distribution balls around the Kalman filter prediction. This is also written over here. So again, B epsilon is a set of all distributions that are epsilon close. In particular, by epsilon close, we mean in terms of the Wasserstein distance. Okay. Now that we have presented the approximate problem, we propose a sampling-based algorithm that we refer to as robust RRT to solve it. First, what we do, as is standard in sampling-based approaches, we sample a mean and the covariance over here. Then we find the closest node to the sampled mean and covariance. In this case, this may be this node, and we connect a new node to the parent node that is close to our sampled node if two conditions hold. First, we need that there exists a control input that satisfies the Kalman filter prediction map. And second, the new node here should satisfy the robustified risk constraints from the previous slide, so including these epsilon distribution balls. Next, we check the neighboring nodes of the newly added node for a cost optimal path. This is also standard in RRT, so we may check other nodes that are in close proximity, and if they give a lower cost, we would select this one. In the meantime, we also check if the goal region is reached, which is not the case here, and then we grow the tree further, and we also perform tree rewiring for cost optimality. So in this case, we might just rewire the tree, and eventually we'll hopefully reach the goal region. Let us now also discuss the properties that our algorithm comes with. First, if a control sequence of use is found in our robust RRT, then the Kalman filter predictions satisfy the robustified risk constraints. And this basically holds by construction of the algorithm. If we now observe output measurements Y, and they are such that the Kalman filter estimate is contained within the epsilon balls put around the Kalman filter predictions for all times, then the control sequence that we have found is even a feasible solution to the risk-aware motion planning problem. The question then is, how likely is it that this will hold? And in the paper, we show that the probability that this actually holds, this inclusion here, depends on the robustness margin epsilon according to this equation. So we have the norm of some function m, I'll define it in a second, minus the mean of the Kalman filter prediction squared is smaller than epsilon for all t. So by choosing larger margins, we increase the probability that this holds. M over here is given by the Kalman filter recursion, in which we now treat y as a random variable. We also show that a good choice of alpha, and we reason about this in the paper, is if we take a time variant epsilon, where epsilon is equal to the induced matrix norm of a to the power of t times a positive constant. Okay, so far we have talked about the offline algorithm in order how to construct a tree, and I'm now going to show a bit how we can use this in an online manner and how we can do replanning. Initially, what we do is we construct a tree to find a feasible set of feasible control inputs, and then we execute these control inputs. We collect measurements all the time. And if the Kalman filter now is within the ball, everything is fine. But if at some point the Kalman filter estimate is outside of these balls, then we need to replan. And as said, the robustness margin epsilon over here allows to control the replanning frequency that we have. So let us also look at the simulations of the paper. First, we consider a linear system that consists of position and velocity as a state. And the sensor is such that we can measure the position, but not the velocity. The specification is to avoid these circles over here, which form a funnel through which the system can converse. The system starts here and has to arrive here. And yeah, we have risk constraints to avoid these regions. All right, what we see here, if we have no robustness margin and no replanning, is that we violate the specification. If we put replanning on top and then for different epsilon values, we see that we satisfy the specification. Here we go through the paths through the funnel in between, and here we pick the funnel that goes around. So the trade-off here is basically that the robustness margin helps us to control the replanning frequency. We see here is a lot of replanning instances, while here we only have one. In this way, the robustness margin allows us to control the trade-off between being conservative and being robust. We also have simulations here with the time varying epsilon that we talked before. Basically, here we see that as uncertainty increases over time, it makes sense to also have the epsilon increase over time. All right. Here we show like how the different RT, the different robust RT trees grow for different epsilon values. And we see for smaller robustnesses, we again take a funnel in between, and for larger robustness, we just take a path around.